Hey, welcome back everyone. Today we're doing more Chapter 7 problems focusing on light. And in this problem here, we're looking at the light that's emitted when electrons change energy levels. So there's different, you can think of the electrons as surrounding the nucleus of the atom, but there's different areas in space where the electrons can occupy. Some are further away from the nucleus, some are closer to the nucleus, and that depends on the energy of the electron. Electrons themselves have energy. Some electrons have more energy than others. So electrons that have more energy are said to be in a higher energy level, which is basically further away from the nucleus. So what happens when an electron goes from a high energy level to a lower energy level? They can go from low to high as well, but in this example we're showing an electron going from energy level 6 to energy level 2. So it's going from a high energy level to a low energy level. That means it's going from high energy to low energy. So basically when that happens, it emits a photon. Like, this is how fluorescence works. When electrons are excited and then they go from high energy to low energy, they emit light because that energy has to go somewhere. Remember, we cannot destroy energy. Energy is conserved. So the energy has to go somewhere when this electron goes from 6 to 2, so it's emitted as light. A photon of light is emitted. And the color of the photon is dependent on its energy. Remember that energy is equal to hc over lambda, right? So the energy of the light emitted, is dependent on its wavelength, right? So basically we can solve here what is the wavelength of light by first solving for energy and then plugging that energy in here and then solving for wavelength. So in this equation we have the change in energy is equal to RH. So RH is Rydberg's constant, and that's 2.18 times 10 to the negative 18 joules per atom. So it's just a constant. You guys won't have to remember that on a test or anything. That'll generally be given to you guys. So we're going to plug that in here, and we have NF, which means final energy. So if we're going from 6 to 2, this would be final and this would be initial, right? So our NF would be 2, our NI would be 6, so that's squared, so it'd be 2 squared and 6 squared. So 1 over 6 squared, sorry, 1 over 2 squared minus 1 over 6 squared. So delta E is equal to our constant over 1 over 2 squared minus 1 over 6 squared. Okay, so basically we can just multiply all of this out, and what we're going to get is 4.84 times 10 to the negative 19 joules. You guys see that? Alright. So this is the energy of the photon that's being emitted when this electron goes from energy level 6 to energy level 2. So that's good. That's 1. That's our delta E, joules, right? Energy. But we also want to look at what is the wavelength of this photon that's emitted. So that's what we want to use our equation over here. We have energy is equal to H. Remember, H is Planck's constant, 6.626 times 10 to the negative 34. So it's H. C is the speed of light. Remember, that's also a constant, 2.99 times 10 to the 8 meters per second. And then This is our wavelength, right? Lambda. Okay, so we're going to take our energy, which is 4.4 times 10 to the negative 19 is equal to Planck's constant. 34 times the speed of light over our wavelength. So this is what we're solving for here. So we want to solve for wavelength. You can write it as x. So basically we're going to do our algebra, divide, both sides by Planck's constant. So those will cancel, and then we'll cross multiply, or however you want to do it, and then you get the wavelength of 4.104 times 10 to the negative 7. So this is meters that you get here, because remember your speed of light is meters per second, right? Meters per second. So if we wanted nanometers, 10 to the negative 9, so basically 410 nanometers. So that would be the wavelength of light emitted by this transition. So there you go, guys. We calculated the energy of the light and the wavelength of the light emitted from a transition. The bigger the transition, the higher the energy, means shorter wavelength. Smaller transitions, less energy, longer wavelength. So I hope you guys enjoyed this video. Give it a like, thumbs up. Give me a comment, let me know what other videos you want to see, what other topics you want me to cover. Alright, until next time, I'll see you guys later. Bye.